Section 5.6 Indeterminate Forms and L'Hopital's Rule. Recall in the previous chapters, we learned that the forms 0 over 0 or infinity over infinity are called indeterminate because there is no guarantee that a limit exists, nor what the limit is even if it does exist. We had a few techniques to determine such limits by factoring, rationalizing, and simplifying complex fractions. In this section, we will learn another powerful technique to find the limits of indeterminate forms called L'Hopital's rule, which is named after the French mathematician L'Hopital. So let's start. Use L'Hopital's rule to evaluate indeterminate limits in the form of 0 over 0 or plus minus infinity over plus minus infinity. The order doesn't matter. You could have an infinity over negative infinity or negative infinity over negative infinity. Any combination of plus minus infinity over plus minus infinity will be considered as indeterminate limits. And when you do, you can use L'Hopital's rule, which says if limit x approaches to a of f of x over g of x equal 0 over 0, or limit x approaches to a of f of x over g of x equal any combination of plus minus infinity over plus minus infinity, then limit x approaches to a of f of x over g of x is equal to limit x approaches to a of f prime of x over g prime of x. When you plug x equal a to the function on the top and function in the bottom to actually evaluate the limit, and if you get 0 over 0 or plus minus infinity over plus minus infinity, then you can take the derivative of top function over derivative of denominator function, and then you can plug a in there. What if that produces 0 over 0 or plus minus infinity over plus minus infinity again? Then you can look at them as new functions and still use L'Hopital's rule. So sometime you need to use multiple times of L'Hopital's rule to evaluate the limit. In the past, we have used the factoring and canceling to handle indeterminate limits. Look at the example. Limit x approaches to 0 of e to the 2x power minus 1 over e to the x power minus 1 equal. If you plug x equals 0 to evaluate the limit, you have e to the 0 minus 1 over e to the 0 minus 1, which is 0 over 0. In that case, you had to factor. So limit x approaches to 0. Note that this is equal to e to the x squared. So you have a squared minus b squared since 1 is the same as 1 squared. So when you factor as a plus b times a minus b, you have e to the x plus 1 times e to the x minus 1 over e to the x minus 1. So e to the x minus 1 factors get canceled. And now you can plug 0 for x. So you get e to the 0 plus 1, which is 1 plus 1. So you get 2. But L'Hopital is saying now, when you try to calculate the limit, if you get 0 over 0, then just take the derivative of a numerator function over derivative of a denominator function, and then you can plug 0 for x. So let's do that now. If you take the derivative of a numerator, this is not e to the x, so it's e to the u. So derivative of e to the u is e to the u times u prime by chain rule. So you get e to the u, your u is 2x, times u prime, since u is 2x, u prime is 2. Derivative of negative 1 is 0. Derivative of e to the x is e to the x. So now you plug x equals 0. Let's see what happens. Then I get e to the 0 times 2 is 0 power times 2 over e to the 0, which is 1 times 2 over 1. So you do get 2. Evaluate each limit. So what happens when you plug 3 in there? You can see that I'm going to get square root of 3 squared minus 9 over 3 minus 3, which is 0 over 0. So you get to use Hopital's rule. So then limit x approaches to 3 from the right. What's the derivative of square root of x squared minus 9? Square root of x squared minus 9 is, if you rewrite it, it is x squared minus 9 to the 1/2 power. So when you take the derivative of that, you get 1/2 x squared minus 9 to the, lose 1 power, you get negative 1/2 power. Chain rule, I need to multiply by derivative of inner function, which is 2x, over derivative of x minus 3 is just 1. So the numerator, you can see that 2 and 2 cancel. So I have limit x approaches to 3 from the right. All I have is x on the numerator. And since x squared minus 9 to the negative 1/2 power needs to go to the denominator, and since 1/2 power is a square root, I'm going to put it back, x squared minus 9. Now, when you plug x equal 3 on the top, it is just 3. And 3 from the right, it's a 3.00001 squared minus 9, which is a positive number, getting close to 0. So you actually get positive infinity. Right limit of this function as x approaches to 3 is positive infinity. How about limit x approaches to infinity of 3x squared plus 2x minus 9 over 6x squared plus 7? Well, x squared terms will dominate these polynomial, both the numerator and denominator, and it will go to positive infinity over positive infinity. So this is indeterminate form that you get to use Hopital's rule. And this will be equal to limit x approaches to infinity of derivative of 3x squared is 6x, derivative of 2x is 2, derivative of negative 9 is 0, derivative of 6x squared is 12x, derivative of 7 is 0. But again, when you plug x equal infinity, you get infinity over infinity. So you get to use Hopital's rule again. So limit x approaches to infinity of derivative of 6x plus 2 is 6, derivative of 12x is 12, limit of a constant is a constant, and 6 over 12 reduced to 1/2. So limit is 1/2. How about limit x approaches to 1 of ln x over x squared minus 3x plus 2? If I plug 1 in there, what happens? I get ln 1 over 1 squared minus 3 times 1 plus 2, which is 0 over 0 again. So you get to use Hopital's rule. So limit x approaches to 1, derivative of ln x is 1 over x, derivative of x squared is 2x, derivative of negative 3x is negative 3. Now, if you plug x equal 1, what happens? I get 1 over 1, which is 1, and I get 2 times 1 minus 3, which is negative 1. So limit is negative 1. Very cool. Last one. What happens when x approaches to infinity of x to the 5th power over e to the x to the 3rd power? That will be infinity to the 5th power over e to the infinity to the 3rd power. Wow, that will be infinity over infinity, right? So you get to use Hopital's rule. So let's take the derivative of numerator and denominator. So limit x approaches to infinity of derivative of x to the 5th is 5x to the 4th. derivative of e to the u is e to the u times u prime. So that will be e to the x to the third power times derivative of x cubed is 3x squared. So then we can reduce x square factor with the x square factor. If you plug infinity for x, again, I have 5 times infinity square, which is infinity, over e to the infinity to the third power times 3 is infinity. So again, since this is indeterminate form, you get to use L'Hopital's rule one more time. So let's do that. Then limit x approach to infinity of derivative of a 5x squared is 10x. And I have a 3 times e to the u. Derivative of e to the u is e to the u times u prime, which is e to the x to the third power times derivative of x cubed is 3x squared. So then now you get to cancel again on x with an x. So what I really have here is limit x approach to infinity of 10 over 9 e to the x to the third power. And since I have a 10 on the top, and when you plug infinity for x, e to the infinity to the third power will of course go to infinity. And when you have a constant on the numerator and denominator gets bigger and bigger and bigger, you know it goes to 0. So 0 is the limit. Second type of indeterminate limit is of the form 0 times infinity or infinity minus infinity. In this case, we're going to rewrite the expression so that it will look like 0 over 0 or infinity over infinity, so that we could use L'Hopital's rule again. So let's look at the example. Limit x approach to 1 from the left of 1 minus x times tangent pi x over 2. So when you do the direct substitution, 1 minus 1 from the left is number less than 1. So when you subtract 1 minus number less than 1, it is getting close to 0, but it is a positive number. And tangent x approach to 1 from the left is tangent pi over 2 from the left. And if you recall, tangent graph looks like that. So as x approach to 1 from the left, tangent pi x over 2 will approach to tangent pi over 2 from the left, which you can see that graph is approaching to positive infinity. And because this is 0 times infinity, why don't we rewrite this as 0 over 1 over infinity? Because 0 divided by 1 over infinity is the same as 0 times reciprocal of that, which is infinity. And that's what you have. Then means we are going to rewrite this as limit x approach to 1 from the left. We will leave 1 minus x on the numerator, but we will write tangent pi x over 2 as 1 over tangent pi x over 2. But what is 1 over tangent pi x over 2? That's right. That's just cotangent pi x over 2. So that will be x approach to 1 from the left of 1 minus x over cotangent pi x over 2. And now this will go to 0 over 0 because 1 over infinity goes to 0. So now when you plug 1 for x, I do get 0 over 0. So you get to use L'Hopital's rule. And I'm going to take the derivative of numerator, limit x approach to 1 from the left. Derivative of numerator 1 minus x is negative 1. Derivative of cotangent pi x over 2, that's a cotangent u. And derivative of cotangent u is negative cosecant square u. My u is pi x over 2 times u prime. And derivative of pi x over 2 is pi over 2. Let's simplify that now. Negative over negative makes it positive. This is an input for cosecant function, so I cannot touch that. However, pi over 2 is constant multiple, so you can put it in the front, and pi stays there. But pi over 2, since 2's denominator, let's actually put it on the numerator. So I have limit x approaches to 1 from the left of 2 over pi cosecant square pi x over 2. And that is limit x approaches to 1 from the left 2 over pi times cosecant square pi x over 2 is 1 over sine square pi x over 2, which is equal to limit x approaches to 1 from the left. This is 2 sine square pi x over 2 over pi. Now I'm going to plug 1 for x. And you get 2 sine square pi over 2 over pi. And sine of pi over 2 is 1. 1 squared is 1. So I get 2 over pi. Let's look at another example. Limit x approaches to infinity cosecant 1 over x times e to the 1 over x power minus 1. If I do direct substitution, cosecant 1 over infinity goes to 0. And cosecant of 0, you have actually vertical asymptote there. You can remember this is the sine graph and cosecant graph is above sine. So it looks like that. And actually the y-axis is a vertical asymptote for that. So when x goes to positive infinity, 1 over positive infinity approaches to 0 from the right. So when you go 0 from the right, cosecant of 1 over x goes to infinity times e to the 1 over infinity goes to 0. So you have e to the 0 minus 1, and that's 1 minus 1, which is 0. So again, I have infinity times 0. So you want to make this to infinity over infinity or 0 over 0. But I can see that cosecant 1 over x is same as what? Right, that's 1 over sine 1 over x. So I can rewrite this so that I have a 0 over 0. So that's how we will rewrite this. This is a limit x approaches to infinity of e to the 1 over x minus 1 over cosecant 1 over x is 1 over sine of 1 over x. So I'm going to now write sine of 1 over x since it went to denominator. And now, because 1 over infinity goes to 0 and sine of 0 is 0, I do now have 0 over 0. So I get to use Hopital's rule. And now I'm going to take the derivative on the numerator and derivative in the denominator. So I have derivative of e to the u is e to the, my u is x to the negative 1 power, right? Times u prime is negative 1 times x to the negative 2nd power over sine 1 over x, that's a sine of u. Derivative of sine u is cosine of u times u prime. And my u again is 1 over x, which is x to the negative 1 power. So it's the same as what you have above. Derivative of 1 over x is negative 1 times x to the negative 2nd power. So right away, since I have a common factors, you can cancel them. And now what I have is limit x approaches to infinity of e to the 1 over x over cosine 1 over x. Can I plug infinity for x now? Let's try. So what happens if I plug x equal infinity? 1 over infinity is 0, so this goes to e to the 0's power. And cosine of 0 is 1. Yay! So I have 1 over 1. So limit is 1. Evaluate the limit. limit theta approaches to 0 from the right of cotangent theta minus cosecant theta. So cotangent theta, if you recall, this is 0 and this is pi, and this is cotangent graph looks like. So cotangent of theta as theta approaches to 0 from the right, then cotangent theta goes to infinity minus cosecant theta as theta approaches to 0 from the right. You just saw it also goes to positive infinity. So you have infinity minus infinity. So let's try to rewrite these so that we can form a rational expression that will give you either 0 over 0 or infinity over infinity. So limit theta approaches to 0 from the right. Cotangent theta is cosine theta over sine theta minus cosecant theta is 1 over sine theta. So that's equal to limit theta approaches to 0 from the right. My common denominator is sine theta. My numerator is cosine theta minus 1. So if theta approaches to 0 from the right, cosine of 0 is 1. So I get 1 minus 1, which is 0, over sine of 0 is 0. So we have established the 0 over 0 indeterminate form. So I get to use Hopital's rule. So now let's take the derivative. So I have a limit theta approaches to 0 from the right. Derivative of cosine theta is negative sine theta. Derivative of negative 1 is 0. Derivative of sine theta is cosine theta. And now if I plug 0 for theta, I get negative sine 0 over cosine 0, which is equal to negative 0 over 1. So it is just 0. So I found the limit. The last type of indeterminate form is 0 to the 0th power, or 1 to the infinity, or infinity to the 0th power. When you have these power forms of indeterminate limits, you are going to use characteristic of logarithm. So first plug the x value to see if you get 0 to the 0th, or 1 to the infinity, or infinity to the 0th power. So let's check. I have a limit x approaches to 0 from the right, x to the x's power. So you can see right away I will get 0 to the 0th power, which is the first case of indeterminate form. When that happens, you are going to let L for limit equal limit x approaches to 0 from the right of x to the x's power. And of course, since that's what the limit is, your goal is to find L. Now you are going to take ln both sides. So take ln both sides, I get ln of L equal ln of limit x approaches to 0 from the right, x to the x's power. Then now you can actually switch function and the limit. So this will go to, you can rewrite as limit x approaches to 0 from the right of ln x to the x's power. Now, the logarithm has a beautiful property such that power of input gets to drop in the front. So you can rewrite this as now limit x approaches to 0 from the right of x times ln x. So now if you plug 0, I get 0 times ln of 0. Do you remember ln x graph looks like that? So as x approaches to 0 from the right, your function is trying to reach it to negative infinity. So you have a 0 times negative infinity, which is indeterminate form. However, I would like to rewrite this again as 0 over 0 or negative infinity over positive infinity. So now, which one should I bring it down? Well, I know derivative of ln x. And if I bring x down, it will be written as 1 over x, which is x to the negative 1 power. And I could take the derivative of that, no problem either. So we write this as limit x approaches to 0 from the right. Let's leave ln x on the top, but x, let's write as 1 over x. So now I have ln of 0 goes to negative infinity over 1 over 0 from the right. That will go to positive infinity. We get to use Hopital's rule now. So let's use Hopital's rule. I do get then limit x approaches to 0 from the right. Derivative of ln x is 1 over x. And this is x to the negative 1 power. So when you take the derivative of that, you get negative 1 x to the negative 2nd power. So let's clean that up. 1 over x times, that will be negative x squared, so that these cancel and you get negative x only. So this become limit x approaches to 0 from the right of negative x is all it became. So now you can plug 0 for x, and limit x approaches to 0 from the right of negative x is 0. And you're not done yet, because what you have from the left, you can see you have natural log of L equals 0 is what you have, and you need to find L. So I got a little bit of work to do to find the L here. So now let's solve that part. Let me use the room here. ln L equals 0. So change this to exponential. You get the base is e to the 0's power equal L, so that L is 1. That was what the limit x approaches to 0 from the right of x to the x's power. So you can conclude that now limit x approaches to 0 from the right of x to the x's power is equal to L, which is 1. And finally, that is your answer. Next example. Limit x approaches to 0 from the right, 1 plus x to the cosecant x power. So if I plug 0 for x, I get 1 plus 0 is 1 to the cosecant of 0 from the right. This is third time we're singing it already from just this section. It went to positive infinity. And now I have 1 to the infinity power. And that's right here. So it is one of those kind that we have to call this limit L and take ln both sides and go from there. So let's go ahead and do that. We're gonna say let L equal limit x approaches to 0 from the right of 1 plus x to the cosecant x power. And then what was next step? Yes, we take ln both sides of limit x approaches to 0 from the right of quantity 1 plus x to the cosecant x power. And then what do? You switch limit and the natural log. So you have limit now x approaches to 0 from the right of ln 1 plus x to the cosecant x power. So then this is equal to limit x approaches to 0 from the right. Remember, we're taking ln so that we can bring the power down. And you're going to have cosecant x times ln of 1 plus x. And you want to check what kind of form you have now. So if you were to plug 0 from the right, cosecant of 0 from the positive, remember that was positive infinity times ln 1 plus 0. And remember, this is what the ln function looks like. And y equal ln x always pass through 1 comma 0. So when x approaches to 0, you can literally plug it in and it will be 0. So you have an infinity times 0 again. So you would like to make it 0 over 0, or you would like to make it infinity over infinity. so that you get to use L'Hopital's rule. Now, remember earlier, we want ln 1 plus x there on the numerator because derivative of that will be just the 1 over u times u prime. And cosecant x2, that's very easy to change it to rational function, right? So let's change cosecant x to 1 over sine so that we could easily make it 0 over 0. So when you rewrite it, I have limit x approach to 0 from the right. I'm going to leave ln of 1 plus x on the numerator, and cosecant x, I'm gonna make it 1 over sine x. So I have a sine x now in the denominator. So when you plug 0 there, ln of 1 is 0 now, and sine of 0 is 0. So I do have a 0 over 0, which is perfectly good to use L'Hopital's rule. So then this is equal to limit x approach to 0 from the right. Derivative of ln u is 1 over u times u prime, and my u prime is just 1. Derivative of sine x is cosine x. So now I'm gonna plug 0 for x. I get 1 over 1 plus 0, which is 1. 1 times 1, which is 1. Cosine of 0 is 1, so you get 1. But that's not the answer, remember? What you have is ln of L equal 1, and L is what I have to find since that's what the limit of x approach to 0 from the right of quantity 1 plus x to the cosecant x power is. So I need to do a little more work here. So let's do it right here again. Then I have ln L equal 1, and the base for ln is e, so that's e to the fourth power equal L. So your L is e, and you can conclude now that the limit x approach to 0 from the right of 1 plus x to the cosecant x is equal to e. And here is your answer. Last example. Limit theta approach to pi from the right, cotangent theta to the sine theta power. So when you do direct substitution, cotangent of pi from the right, cotangent, here's a 0 and here's a pi, and it looks like that. So cotangent pi from the right, it is positive infinity. Pi from the right, it is going to positive infinity. Sine of pi is 0. So I have infinity to the 0's power is what I have, and that is the last one on this indeterminate form. So let L equal limit theta approach to pi from the right of cotangent theta to the sine theta's power. What do you do next? Yes, take ln both sides. So you have ln L equal ln of limit theta approach to pi from the right of cotangent theta to the sine theta's power. And then what do? Switch ln and the limit, and you have ln L equal the limit theta approach to pi from the right of ln cotangent theta to the sine theta's power. Then we get to use the property of logarithm. So sine theta's power comes down and it becomes sine theta times ln of cotangent theta. So now sine pi is 0. You have a 0 times ln of cotangent pi from the right. You saw cotangent pi from the right is infinity, and ln of infinity, remember this is a ln function. So when input goes to infinity, ln function is also goes to infinity. So you have a 0 times infinity. So you would like to make it 0 over 0 or infinity over infinity, but I would like to keep ln on the top so that I know how to take the derivative of ln u. So let's just do that. So we're going to rewrite sine theta as 1 over cosecant theta. So you have a limit theta approaches to pi from the right, and I have ln of cotangent theta over cosecant theta. So I do know ln of cotangent theta, we just said it was infinity, over cosecant theta, when theta approaches to pi from the right. Remember, cosecant theta is above and below of a sine. So this is what the cosecant looks like, and this is where the pi is. So when you approach pi from the right, cosecant will go to negative infinity. That's okay. Infinity over negative infinity. We also get to use L'Hopital's rule. So let's go ahead and take the derivative of numerator and derivative of denominator now. So you have limit theta approaches to pi from the right, and derivative of ln u is 1 over u cotangent theta times u prime. Derivative of cotangent theta is negative cosecant square theta over derivative of cosecant theta is negative cosecant theta cotangent theta. So let's do some little bit of algebra here. I get to cancel the negatives. So let's turn negative turns into a positive. Cosecant theta, one of the cosecant theta get to cancel. Can we just do it on the side here? 1 over cotangent theta is tangent theta. Tangent theta is sine theta over cosine theta times cosecant theta is 1 over sine theta over cotangent theta is cosine theta over sine theta. So these get to cancel again, and I have 1 over cosine theta times the reciprocal of denominator, which is sine theta over cosine theta. So this simplifies to sine theta over cosine square theta. So all I have to do is now to find the limit theta approaches to pi from the right of sine theta over cosine square theta. So let's plug pi in there for theta. Then I get sine pi over cosine square pi. And sine pi is 0. Cosine of pi is negative 1. But you have a negative 1 times negative 1. So you get positive 1. And 0 over 1 is 0. But that's not the answer again, right? What I have is ln of L equals 0. And I have to find what the L is, since that's what the limit of theta approaches to pi to the right of cotangent theta to the sine theta power is. So we are going to actually figure that out on the side again. I have ln L equals 0. And base for ln is e to the 0's power equal L. So L is 1. So I found the answer, right? Limit theta approaches to pi from the right of cotangent theta to the sine theta's power is indeed 1. And you found the answer. Alright guys, this is everything for 5.6.